Hello students, today's topic we are going to start the CMOS inverter. As you may be knowing, the inverter is the most primitive form of the CMOS digital circuits, especially the digital circuits component. So this is what we are going to do today, and we will look into more details on the inverter and its current characteristics. And using the current characteristics, we will have a look at the output versus the input characteristics, also called as the transfer characteristics of the inverter circuit. So if one can understand the inverter DC characteristics and the transfer characteristics, DC characteristics represents nothing but the current versus the voltage profile. If one can understand that, then the student should be able to appreciate and understand the other digital circuits and its DC and the transfer characteristics. Right. So we will begin with the inverter characteristics and see how it goes. So the inverter is, as you may be knowing, it is formed of the Nmos transistor and then the Pmos transistor. Now this is one such circuit where the Pmos is there, Pmos is in series with that of the Nmos, and where the Pmos is connected to the VDD rail. VDD represents a higher voltage rail, and then the Nmos is the connected to the ground rail. So let me use my pointer so that I can direct the pointer to the specific points in the circuit. So this is basically the inverter circuit where the Pmos and Nmos transistors are in series. And this particular VDD, which is a higher voltage rail compared to that of the ground. So rail in the sense, so what in most of our digital circuits design, we will be using or we'll be calling the rails as nothing but a power supply. We call it as the rails. The reason being, the rails is defined for the transistor when it actually goes into the layout. Right? When we fabricate, we have a metal line which is powered by VDD rail, which is powered by one particular power supply, and another one, the ground metal line, which is connected to the ground power supply. And that is how the term rail has been defined for the digital circuits. In some of the cases, you might see, not only some of the cases, but also in few other cases where you will see multiple rails. What it really means is you will have multiple power supplies. You will have multiple power supplies connected to the multiple metal lines. Right. So one such case could be a different VDD rails where you have VDD1 or VDD2 and VDD3 and so on. Right, so those are the different techniques which have been evolved over the times for several purposes, for several applications, like to improve the performance or improve the power, to save the power, or to save the leakage or improve the leakage and get those benefits to that particular digital system design. Anyway, so coming back to this particular topic where we will have only one power supply, which is a VDD. And the ground of that power supply is disconnected to this particular ground of the circuit. The question is, if I really want an inverter, how do I connect this Pmos and Nmos transistor? So if I actually connect this Pmos, Nmos transistor closer to the ground rail, and then the Pmos transistor closer to the VDD rail, and have them connected together, that means that they are in series, and the Pmos will be closer to VDD rail and Nmos is closer to the ground rail. Then I should be able to get the inverter output. If I actually swap those positions of the Pmos and Nmos, I may not get the inverted output. Right? The inverted output means if V input is high, the output should be low, and if V input is low, the output should be high. Right? So if I swap these two particular positions of Pmos and Nmos, I will not be able to get the inverted output, and that is why we will have this particular circuit. Just to make a point, if I actually swap these positions, I'll actually get a buffer circuit. I will actually get V out to be following the V input, but it is also a very bad buffer design, and we will come to it, or we will have a deep analysis on that sometime later. Right. So coming back to this particular inverter circuits where I have the Pmos and then the Nmos connected in series, although the input, the input that means the gate of those two transistors, the Pmos as well as the Nmos are connected, are tied together, and that has been supplied with the input voltage, V input. The output is, whatever is the common point here of the two transistor is probed as the output voltage. Now, if I want to actually label, the source, drain, and the gate terminals of both these transistors, right? So let's pick the NMOS transistors and let's try to label this, right? So what I'm doing is I have this NMOS transistor where I need to define the gate, right? I need to define which one is source, right? Which can be represented as S, and then I need to define the drains, right? So for an NMOS transistor, we know that the drain has a higher potential than that of the source. So the source indeed should have a lower potential than that of the drain. So that source should be connected. So if I have a power supply of VDD and ground, I might as well connect the source with that of the ground potential. The gate is anyways is an input voltage, so I'll connect this to the input voltage. Right, so that's what I have done here. So I have labeled my source, which is a terminal which is connected to the ground, is labeled as source here. And anyways, the gate is nothing but the input voltage that has been feeding into the gate terminal of this particular transistor. So if this is the source terminal, the other side of this transistor should be the drain. Right, so G, D, and S represents the gate, drain, and the source terminal. On the Pmos side, okay, the representation or the notation of the Pmos is nothing but very similar to that of the Nmos, just that at the input side it is a bubbled input. All right, so this is what we will have. So this is how the Pmos transistors are denoted. And let's say source and drain, again the same thing, and then we know where the gate should be also, right? So for Pmos, we know that the source should be at a higher potential than that of the drain, right? The source should be at a higher potential, so this should be at a higher potential than that of the drain. So if the Pmos is actually tied between this VDD rail, so the Pmos is tied between the VDD rail and that of the common terminal here. In fact, this particular transistor, if we look into it, one side it is the VDD rail, the other side it is the ground rail. So this particular potential can in fact reach to a maximum of this VDD or the minimum of this particular ground. Right, so the output voltage here, whatever I have taken from these two terminals which are connecting to each other, the terminal of the Pmos transistor and the terminal of the Nmos transistor, which are connected to each other. So this particular output node, whatever I'm saying at this point of time, this particular node potential can reach a maximum of VDD and then a minimum of 0. Right, so this particular node potential cannot go beyond VDD. Right, although it cannot go beyond VDD for a particular constraints, so we will have a look at it later. Let's say that the V output or this particular node cannot go beyond VDD, right? So for this particular transistor of the Pmos, the highest potential is actually VDD. On the other side, it will be lower than VDD, or it can reach a maximum of VDD. So it's better to have the source here, which is connected to the VDD, and then the drain side connected to the the node where the Nmos transistor, the other terminal of the Nmos transistor starts. Right. So what it means is, for this particular transistor, we have the gate terminal here. We have the source, the terminal which is connected to the VDD, that is the source, because the source is a higher potential than that of the other terminal, and the other terminal is the drain terminal D. So that's how we have labeled this. So that's how we have labeled the source, drain, and gate terminals for the Pmos and Nmos transistor, which are in series, right? Although the gates are connected or tied together, The drain terminals here, the drain terminals of both NMOS and PMOS are actually connected in series. Okay. And we will see what should be the output voltage with respect to the whatever is the input fed, what should be the output voltage. Right. So that's what our aim is in this particular lecture. We need to find out what is the output voltage given an input voltage. Right. Given an input voltage ranging from 0 to VDD. Right. So if the input voltage is VDD, what should be the output? If the input voltage is 0, what should be the output? If the input voltage is VDD by 2, what should be the output? If the input voltage is less than VDD by 2 and greater than 0, what should be the output voltage? And then so on. Right. So one such, we should be able to find out the output voltage if we can identify the currents, right? If we can identify or write an expression of the current. So this current of PMOS and then this current of NMOS, right? And why I'm writing the current equation here is, or I'm drawing the current for the PMOS and NMOS here is because both these transistors are in series and thereby this current should be same. And if this particular current is same, given an input, I should be able to write an expression for this particular current of PMOS. Given an input, I should be able to write an expression for the current of the NMOS, equate it, and I should be able to find out what is the output voltage. Right? Hope this is clear. Right, so given an input voltage, I should be able to find out what is the output voltage. And if I vary the input voltage, my current will vary, and thereby it should be able to find out what is the output voltage. It becomes very interesting if we can draw the current versus the input voltage profile, or the current versus the output voltage profile, as well as the output versus the input profile. Now, how do we get the current values, and how do I draw or derive the current expressions for the PMOS and in the NMOS transistors? So that's what I have actually put here in NMOS and in the PMOS. I have drawn a barricade here. And then written down the current and then the current expressions for the NMOS, the current expressions for the PMOS. Note that the current expression for PMOS and NMOS, there are two different modes. In fact, there are three different modes. One is the cutoff mode, another one is the linear, another one is the saturation region. Right. So the cutoff region is very, very simple. The current should be 0 in the cutoff region. Right. Whenever the voltage, the input voltage or the VGS value for the NMOS is less than 0.3 volts or the VT value, then the current is 0. And for the VSG for the PMOS, if it is less than VSG, if it is less than 0.3 volts, then it should be the current should be 0 for the PMOS. Right. So assuming that the transistors will be in linear or the saturation region, I need to find out. We're always writing the current expression in terms of VGS and VDS, right? So the current is always a function of VGS and VDS. So what I'm going to write is, the expressions of VGS and VDS in terms of these two new variables, like the V input and then the V output. Okay. So VGS, so if I'm picking the NMOS, that means this particular transistor. So this is my NMOS. Right. So if I'm picking this particular NMOS transistor, the VGS is nothing but, in terms of V input as a variable, it is nothing but V input. And VDS in terms of the variable V output, it is nothing but V output minus the ground rail, which is nothing but V output. Similarly, VGS for the NMOS is nothing but V input minus 0 is nothing but V input. The current, this particular current of the NMOS, IDS of NMOS in the linear and saturation equation. Let's go to the saturation because it is much simpler. You have less number of variables. So IDS saturation of the NMOS is nothing but beta n by 2 multiplied by VGS minus VT the whole square. So because VGS is nothing but V input, so I have written it as V input minus VT the whole square. And IDS, the current, the linear current for the NMOS transistor is nothing but beta n into VGS minus VT minus VDS by 2 multiplied by VDS. Right. So in terms of VGS, instead of I've replaced this VGS variable with that of the V input and then VDS variable in terms of the V output, and that's how I'm getting this particular current equation. So this is the current equation of the linear, and then this is the current equation of the saturation, right? And then similarly, if I want to find out the current expression for the Pmos transistor, which is nothing but which is there closer to the VDD rail, right? And then I know what is the terminal labeling as source, drain, and gate, right? So the current, we know that it is nothing but in the linear and saturation region, I will have the VGS and then VDS of the Pmos variable, right? Of the Pmos variable, and if I can somehow replace those variables of VGS and VDS in terms of V input and V output, then I will have both these currents, Pmos and Nmos currents, right, written or expressed as a function of V input and V output, right? So that's what I want. So we will derive the VGS for the Pmos. VGS for the Pmos is nothing but in terms of V input and VDD, V input minus VDD. And VDS for the Pmos is nothing but V output minus VDD. That's what I've written here. IDS of the Pmos saturation is nothing but beta Pmos. So beta Pmos divided by 2 multiplied by VGS minus VT the whole square, right? So VGS, which will be nothing but VGS VDD minus V input, or rather, you can write it as, this one is nothing but VSG minus the mod of VT of Pmos, which is nothing but, VT is, as I've said earlier, VT for the Pmos is always minus of 0.3. So I've taken the mod of it. So it will be minus of 0.3, the whole square, right? So this is what I'm assuming. So this beta P by 2. Right, so VSG is denoted or expressed as VDD minus V input. So that's what comes here. And so this particular expression of the Pmos current in saturation is nothing but beta P by 2 into VDD minus V in minus of mod of VT, the whole the whole of the square. Now the IDS current for the Pmos linear region, when it is in the linear region, it is nothing but beta P into VSG minus the mod of Vt of Pmos minus VSD by 2, the whole multiplied by VSD, right? So the same thing I have written here, VSG, which is nothing but VDD minus V input minus the mod of VTP minus VSD by 2, which is nothing but VDD minus V out, the whole by 2 multiplied by VDD minus V out. So now I have both the currents of Nmos and Pmos, which are in series, right? The currents should be same, but expressed in terms of V input and V output and VDD. Of course, VDD will not be a variable, it will be a constant value, right? So I have now the current equations in the form of V input and V output. Hope this is clear. Moving on, we had expressed the current expressions of the current equations in terms of betas, beta n and beta p. So if I have a closer look at beta p or beta n, it is nothing but mobility multiplied by the width of the transistor multiplied by the C oxide divided by Ln, right? Which is nothing but the channel length, right? So the channel length, in fact, for the Pmos and Nmos, for a particular technology node, we are not going to change the channel length at all. So this remains constant. In fact, Ln and Lp will be same. So Ln, the Nmos channel, and then the Pmos channel will mostly be the same. That's how the fabrication process doesn't allow us to change the channel length. What we can change is the W, the width of the transistors, the width of the transistors of the Pmos and Nmos. C oxide again is a constant. So the C oxide, if you remember the C oxide for both Nmos and Pmos, it is nothing but epsilon naught, the K of oxide, which is 3.9 divided by the T oxide, right? So this is a constant, this is a constant. T T oxide for a fabrication process, again for a particular technology node, it is a constant. So this being constant, so C oxide will be a constant value for both NMOS and PMOS. Right, so T oxide we cannot change we cannot have a T oxide for a NMOS separate or different than that of for a PMOS. So my C oxide will also be the same. Mu for NMOS and mu for PMOS, right, will be different, but again it will be for an ideal long channel behavior or a model, it will be a constant values. Although the PMOS, we effectively take it as close to half of that of the mobility of the NMOS, right? So in that case, if I want the beta N and beta P to be the same, right, if I want to be the same, right, and mu, the mobility of holes is half that of the mobility of the electrons, so then I need to increase the width of the PMOS, right, appropriately. In such a case, if I scale the width of the PMOS such that it is twice that of the width of the NMOS, then I will have this betas of the NMOS and the PMOS to be the same. And so the advantage of having this beta NMOS and PMOS to be the same is I'll get, and if I go back to the slide of where I had written the current expressions, so if I look into the saturation currents, right, this betas, if it is same, the betas if it is same, the betas here if it is same, and the way I can make it same is because the width of the PMOS is made twice that of the width of the NMOS, and then I will have this betas to be same, and thereby I will have this current equated, and then I should be able to find out the V, the V input, or rather, if I make this betas to be same, right, and if I am equating the currents, right, I don't know whether it will be the saturation of PMOS and saturation of NMOS will be equated, or linear of NMOS and then saturation of PMOS will be equated. And there I should be able to find out the V out as a function of only V input, right? So what we are trying to do here is we are making the betas to be the same, not necessarily that the betas will always be the same. So if I want to change the width of the NMOS and then the PMOS, it is not necessary that the betas will always be the same. But just for the primitive calculations, I am taking a very simplest case, making the betas to be the same, and then trying to see what happens to the output as a function of input, or input as a function of output. All right. Okay. So coming back to this particular, the slide of the inverter where we had the PMOS and NMOS in series. This particular VDD, let's, for time being, let's say that we will fix it to 5 volts. Generally, for a 65 nanometer technology node, which we will generally use, right, the VDD values are generally 1 volts, not more than that. Maximum of it will go to 1.2. The minimum it might go is 0.8 volts, right? But here I am taking a very, kind of a scaled VDD, so that I should be able to see the solutions much more at a little bit at a higher voltage, right? So practically most of the examples of the 65 nanometer technology will always have it as 1 volts. But just for a theoretical understanding, I'm just taking it the 5 volts. So what it implies is my input voltage can actually, I can actually put the input voltage from 0 to 5 volts, right? Not beyond that and not less than 0 volts, right? It cannot go beyond 5 volts. It cannot go less than 0 volts. So if I have this 0 to 5 volts, that means if the input voltage is 0, what should be the output voltage? What should be the current? What should be the current here? What should be the current here? If the input voltage is 1 volts, what should be the current here? What should be the current here? What should be the output voltage? If the input voltage is 2 volts, what should be the current here, and output voltage? If the input voltage is 5 volts, what should be the current and what should be the output voltage? And we have anyways have this current expressions, right? And so if I actually, in the last slide we had expressed this VGS, VDS in terms of VDD. So now I will replace this VDD with that of the 5 volts, replace this VDD with that of the 5 volts. And And that's what I have put here. VGS of Pmos is V input minus 5 volts and VDS of Pmos is V out minus 5 volts. Okay, hope this is clear. Okay, so we are now in a position to draw the current versus the output voltage. Right, so what it means is, for a different VGS values, how should the current and then the VDS profile looks like. Now what we really want is the DC characteristics of an inverter, right? So if I go back to the previous slide, what we really want is the current here, which is same because both the transistors are in series, right? With respect to the different V output voltage, right, for a specific values of V input voltage. Right, what we really want is an inverter. If I apply an input here, what should be the output voltage and what should be the current? That's what we want. What we are going, the way we are going to achieve this is, we would like to have the current expressions of the Pmos and of the Nmos. Right, if we know what is the current expression of Pmos and what is the current expression of Nmos, for that I need to know what expression of Nmos I need to write, whether the linear region expression or the saturation region expression, and equate it to that particular Pmos current, right? Where we need to know that whether the Pmos is in saturation or the linear region, right? So I can actually equate this to this, or I can equate it this to this, or I can equate it to this to this, right? Or I can equate it to this to this, right? So there are 1, 2, 3 and 4. So if I have those 4 equations evaluated, I should be able to know for a particular V input voltage, what is the current, what is the solution current, and what is the solution output voltage. Right now, for example, if I actually equate, let me take one such example. If I equate this current, and let me say that I'll equate this one, right? And if I equate this, the current, if I equate it, because both the transistors are in series, I will have V input, this V input, right? So V output, I will have the V output in terms of the as a function of V input, and I can make some judgment about it. All right, but if you do this particular mathematical equation, so what I meant was the V output as a function of V input, and if I know what is the V input value, I should be able to estimate what is V output. All right. So what we can do is, if we can have some kind of a judgment of whether the Nmos will be in linear or Pmos is in saturation, or Pmos is in linear or Nmos is in saturation, or the vice versa, whatever it is, I should be able to equate those two expressions, right? But to start with, we really don't know what is, whether the Nmos or Pmos is in saturation. It actually depends on this particular V output. If I look at it, it actually depends on this V output, and V output is a variable itself. Now we don't know whether it is closer to VDD or closer to the 0 volts, or it is, if this is 5 volts, whether it is 2.5 volts or 1 volts or 2 volts, right? So in that case, if we really don't know at this particular point of time, with some experience, we should be able to, match those currents. But at this point of time, when we are very inexperienced, why don't we draw the current versus the output voltage profiles of the Nmos and Pmos graphically, and wherever those profiles of the currents intersect, the Pmos and then the Nmos current, if they intersect, that means the Nmos and then the Pmos currents are same at that particular point, right? That particular point will give me the V out and then the V input. Right, so if we don't know the modes or the regions of Nmos and Pmos transistor, one way to find out the solution of the current and then the output voltage and the for a given input voltage is to graphically draw the Nmos characteristics, graphically draw the Pmos characteristics, and then somehow try to intersect, right, the IV characteristics of the Nmos, IV characteristics of the Pmos, Wherever that intersection happens, we know that the currents are same. So those particular voltage values will give me the V output voltage. Right? So that is the overall aim. So to begin with, what we are doing is, I have the Nmos transistor. So this is connected to ground, and then this is nothing but the output voltage, right? And then we have the gate voltage here, which is nothing but feeded with the input voltage. This is the source, this is the drain, as I had written as per my labelings, right? So in this particular case, for an Nmos transistor, I know that for a different VGS, I should be able to find out the IDS profile for for the VDS, or rather I should write it as IDS versus VDS for a particular value of VGS, right? So for an Nmos transistor here, so this is nothing but an Nmos transistors, standalone Nmos transistors profile, right? So given in fixed input, what should be the VDS, what should be the IDS for a different values of VDS? So this is what I have written: the linear region, saturation region, linear region, saturation region, linear region, saturation region, linear region, saturation region, linear region, and saturation region, right? So the linear region, saturation region for different values of VGS, right? So in this particular case, let's take that Vt is equal to 0.3 volts for the Nmos as well as for the Pmos. So for the Nmos is equal to, I'm going to write it as Vtp of mod is 0.3 volts, right? So anything, if V input is 0, we know that the current will be 0. So this particular line, which is parallel to the x-axis, is my 0 current line when the input is 0. If the input is 1, that means VGS is actually 1 volts. I'll get this particular current profile. So up till this particular value when VDS is, so this particular value will be VDS saturation, right, which is nothing but 1 minus 0.3 volts. That means 0.7 volts. Up till that it will be linear, and after that it will be saturation. Similarly, VGS of 2, right? V input, when V input is of 2 volts, VGS of 2, this is a different VGS value. I'll get the saturation current, I'll get the linear current. Again, this particular value turns out to be, and if I pick this into the VDS axis, right? So this particular VDS value will be nothing but 2 minus of 0.3, that will be 1.7 volts. Similarly, I should be able to find the current versus the VDS profile, for a different VGS. Now VGS is 3, VGS is 4, VGS is 5. I should be able to draw the current versus the voltage characteristics. All right. Remember, if I have drawn this as IDS current, so this is nothing but the IDS of Nmos. Okay. So IDS of Nmos, this is the current I'm talking about, IDS of Nmos. And if I write the VDS, it is nothing but V out minus 0. So that's why this particular axis I have written it as V out. Okay. So for different values of VGS, we are drawing the IV characteristics, the IDS current versus the VDS. So the IDS is nothing but the IDS of Nmos, and VDS is now rewritten as V out minus 0, which is nothing but V out. And these particular values, VGS1, VGS0, VGS1, VGS2, VGS3, VGS4, VGS5 is relabeled as V input of 0, V input of 1, 2, 3, 4, 5. Right? This subscript of 4, subscript of 3, subscript of 2, 1 and 0, and then 5 here represents that the input voltage, I'm applying an input voltage of 5 volts. So VGS will be nothing but 5 volts. If I'm applying an input voltage of 4 volts, VGS will be nothing but 4 volts. And if I'm applying an input voltage of 3 volts, VGS will be nothing but 3 volts. If I'm applying an input voltage of 2 volts, VGS will be nothing but 2 volts, and then so on.